Yeah. So lecture 28. Let's see. I guess I can start. People will show up late. Do you have any questions from last lecture? I'll review it as usual. So we started doing the simplest example of there were at one loop there were three diagrams in QED that we needed to do. The Fermion loop, it's a vacuum polarization. It's called vacuum polarization. There is the vertex correction, which is this. And then there is the correction to the propagator of the fermion. So we focus on this one, and I'm going to review that. We almost finished the calculation, but some interpretation is needed. There's this diagram that I will discuss today, and maybe we'll chat a little bit about this diagram as well. But the principle that we're going to go over for this, I'm going to repeat them again because it's the same sort of structure that appears in every gauge theory for sure, and every theory QED-like theory. So those of you guys who do the part 2 of the course, for non-abelian gauge theory, we also do a similar thing. There are more diagrams, but the essence of it is the same. So we started by talking about the vacuum polarization of one loop. We talked about the 1pi diagrams. These are the diagrams that if you cut once, they will not be split into 2 parts. So of course, so there will be the propagator, there will be the mu and nu, because these are photons, and these are basically the polarization vectors. Now, it follows from the fact that photon has only 2 degrees of freedom. It has to be that one of the degrees of freedom is completely redundancy. It's silly. It could be integrated out completely. The other degree of freedom is also unphysical, and word identities tell us that it should satisfy this relation. The diagram should satisfy this relation. The amplitude should satisfy this relation to make sure that there is no. Oh, sorry. What am I saying? Well, whatever is the. There will be word identities. Make sure that the external legs are all do not have any degrees of freedom along the propagation of the photon. So in this case, the word identities will tell you that you're gonna have m mu nu is going to be proportional to this object that projects out the or pi mu, sorry. Component along this propagation direction, and then we call this pi f squared. We said that if you naively use a momentum cutoff, you will break the gauge invariance. So word identity will not be satisfied, and to make sure that they are satisfied, because it's important, we use dimensional regularization. So it's a regularization scheme that preserves gauge invariance. Of course, it came at you always have to introduce a cutoff, a scale, physical scale. Oh no. Okay. All right. Can't write now anymore. Wow. All right. It's the last lecture. It's okay. What was I saying? So yeah. So it comes at the cost of now I cannot circle anything. Oh, thank you. Well, I have to let's see this connect and you have to connect it. Let's see. Yeah, I'll figure it out. Pointer would help maybe, yeah. Okay. So it comes at the cost of introducing a scale, that length scale mu. And that is normal. Any regularization will come with a scale, right? There will be a scale, and we talked about the idea of renormalization or separation of scales is that the low energy physics, the physical observables of the theory would be independent of the scale, right? So, for instance, the physical observables of the theory, right, are going to be related to how much, what one physical observable is the running, we saw that, the running of charge, how much the charge runs as we go from what scale 1, let's say q squared to 0. And when we looked at that running, we're going to repeat that again, it will be independent of the cutoff. The epsilon term will cancel, right? All right. Yeah, there's a length scale. What we do is that we modify the integration over space-time to d plus 1, and we're going to be working in primarily sorry, my d here is 3. In 4 minus epsilon space-time dimension. Well, yeah, I'll come back to this. We use a set of, but we do not change the propagators or other ingredients of the Feynman diagrams. Only we have to just make sure that if you have gamma matrices, you use the representation of gamma matrices in d space-time dimension, d plus 1 space-time dimensions. There are a couple of relations between them that we'll have to modify, but we mentioned. So we used Feynman parameterization and Wick rotation to perform this integral. We massaged this integral. What we did was with Feynman parameters introduced, it was an expression for 1 over AB as d of x from 0 to 1 over ax plus b 1 minus x. I think this was my convention. You have an integral over q, not q, what is a k, I guess that's the my notation. Is that what I'm integrating over? Yeah, k. So you introduce this Feynman parameterization, you change the order of integration. After you do that, after a change of variables, you could perform the integral over k inside this integrand of x, right? You do that. And the final answer, when you do the integral, you're going to get a bunch of gamma functions, if you recall. And this is your answer. Your answer is I pi mu naught q comes out. So what is outside? Let's just go through it. There's a e squared term. That's because there are 2 vertices. There is vd plus 1. That comes from the fact that we're doing an integral of d plus 1 of k, right? So the sphere, you do this in radial coordinates. We're in Euclidean coordinates, so that comes out. That 2 pi to the power of d plus 1 is just Fourier transform of the integral that comes out. So there will be 2 terms. This is what okay. I can't point. There will be the term that's proportional to eta mu nu, and then there is a term proportional to p mu nu. P mu nu is precisely this object, the thing that is that projects out that satisfies the word identities. The second part does not satisfy the word identities, and much worse is true divergent. We did the counting of the divergences. We saw that the first term that I've highlighted as order before doing the k integral, this was 1 over k squared, right? And sorry, 1 over lambda to the power 4, cut off lambda to the power 4. So this term was log divergent. Hence, this term was log divergent. The second term was like it diverges like lambda squared, like the cutoff square, and it's also it was awfully violates gauge invariance as well. We saw that it cancels out. It was important, right? When you announce it, we continue cancels out. All right. So the only term that survives is really this this p mu nu term, and now you can take the p mu nu out. Sorry, there are two. Yeah. Then you end up with this pi of q squared, right? So this pi of q squared is the result that remains. Next, we're gonna do is that because this log divergent, we're gonna expand it in 4 minus epsilon dimensions. Now, in this expansion, it will be finite, right? Hopefully that's clear. So what we're gonna do is we're gonna keep the 1 over epsilon term, that's the divergent piece, and the constant term. The epsilon order term, we're just gonna drop it. We don't care, right? All right. Now it's important to notice the structure of it. So the coefficient of this is 2 over epsilon. That's the divergent term. Let's keep that in mind. Then the correction, order 1 correction, has e to minus gamma mu squared 4 pi e to minus gamma. This comes from the expansion of gamma functions, right? But the structure that's important is mu squared over delta. So you have that logarithm mu squared over delta. It's conventional. So remember what this delta was? Unfortunately, I have not written it here. So let me show you what delta was. This delta is is this thing. Actually, maybe these slides have more details, so maybe I should go through them. Right? Wait, did we do this or not? Did I not go over it? We did. Okay, so let me do this again. So this was the expression for pi mu nu, right? There's the most divergent term that drops out. We use the gamma functions to simplify things. I went over this, all of this, and here's your final answer, right? Before I do an expansion in 1 over epsilon. So it has the right properties. It's convergent in space-time dimensions less than 4, and it's transverse as required by gauge invariance, right? This is what I was just flashing. Next, what we did was we expanded this in, remember that W thing was D plus 1, this W that I had up here? This W minus 1 is D plus 1 over 2 minus 2. So that when you expand it, and 4D plus 1 is 4 minus epsilon, this is the expression you get. Good. So it's pretty clear. So what I'd written before was that when you expand this is to a power of minus epsilon over 2. Right? This is what you get. Did I go over this last time or not? I don't remember. I did? This is the expression I just started with, right? But let me write it, copy it on the board, because I think there are a couple of things that are important. There's something called MS bar scheme. I mostly will cover it next in the next course, but let me minus 8 alpha over 4 pi. Integral of g of x 0 to 1 x1 minus x. Then there is the 2 over epsilon log of 4 pi into minus mu. Is that right? Gamma, sorry, gamma mu squared. Gamma mu squared over delta. Good. All right. Gamma. This is just a constant. So you could view this as ln of this constant plus ln of mu squared over delta. Often people eat this ln of this into this term. We'll talk about this later as MS bar. Well, I don't know what later is, next semester. MS bar scheme. But this is the term that remains. We're gonna play with this, right? So we're gonna deal with, forget this about this for a second. We're gonna deal with 1 minus x ln of mu squared over delta. All right, this is all good and nice. All right, so let me write down. So this is 2 alpha over pi, right? Minus 2 alpha over pi. Look at the last line of my equation, right? The equation on the last line. So it's minus 2 alpha over pi. And here I'm plugging in explicitly what mu squared that is. So this was q squared minus x minus, no, that's not q squared. Mu squared. Let me see. I'm actually going back for the. Why am I? I think I should go back to the previous file. Yeah. No. Sorry. Yeah. Okay, so let me remind you what this calculation was about. 1 pi. So bad that I cannot draw pictures. Yeah. So this diagram, the way we interpret this calculation, the way we interpreted it was we interpret this as a renormalization of charge, right? There was a 1 pi thing that we interpreted that, and we split it into e's, right? So this is supposed to, because what is alpha? Alpha is e squared over 4 pi, right? So this has to do with the renormalization of charge, right? So, well, this has to do with normalization of charge, but then this has divergences. What sits outside is the bare parameter. So it's changing by an infinite amount. So what you want to do is you want to calculate pi of q squared minus pi of 0, or q1 squared minus pi of q2 squared. Because both of those calculations would be physical, whereas this guy is non-physical. When you subtract them, the divergence is canceled. This term also cancels. It's pretty clear, right? This term also cancels. So you'll be dealing with this mu squared over delta, right? That will be the subtraction you will have to do. All right, so let me I'm jumping around back and forth. All right, good. So to do that, we define this pi of q squared, which is pi hat of q squared, which is pi of q squared minus pi of 0. This thing is not finite. Each of them had ln of mu squared over delta. So you cancel the mu squareds. So you end up with 2 deltas. Delta above and below, right? ln of delta of 0 and x and q squared and x. All right? Good. What delta was, yeah, I think I would have put m squared here. What delta was, this was m squared. So now here I'm writing pi hat q squared. Right? M is the mass. This is what we ended up with. This tells you about how much renormalization happens to a charge going from q squared to minus q. There's a square root as well over the whole thing. Right? So we're gonna massage this, but I'm gonna pause for and ask for a question. This is finite. Q dependence goes in here. Why do I not do the integral immediately? Can you tell why I'm not doing integral immediately? Well, there are a couple of reasons. First of all, it's ugly. But this has to do with the incoming momentum, right? So we've integrated over K, right? So this is that Q. M squared is just mass of the fermion, right? And this is the integral we have to do. Now, you notice something. Something funny happens here. If m squared is larger than x times 1 minus xq squared, this is finite. Otherwise, we have a little bit of a problem. Do you know what this is pointing at to? There is a branch cut. The branch cut is at q squared equal to 2m squared. This is where the branch cut is. Can you tell what this is, the physics of this? Something weird happens when the incoming photon has energy, which is twice the mass of the fermion. You could pair produce on shell. Something happens over there. When your fermion, your incoming photon doesn't have that much mass, you still have a diagram, but it's never on shell. Right? But now it could be on shell. So if you have enough energy to pair produce, something happens. That's the first observation. All right. What happens is that it's no longer real anymore. Right? There will be an imaginary part. So let's calculate the imaginary part. This is the branch cut. Right? What we're going to do is we're going to subtract the we're going to calculate the discontinuity. Imaginary of pi q squared plus minus I epsilon. Good. All right. What does it end up being? This is the expression for it. You just do the calculation. But now there's an interesting observation. So let me pause. Is the pair production threshold business clear? The calculation is fine and easy and nice. Everything is easy to interpret if q squared is not enough to pair produce. But when you have enough, if at higher energies, there's some subtlety that comes up. This could be imaginary. So let's calculate the imaginary part as we did. We calculate the imaginary part and we find this expression. The same exact expression appeared in the total cross section. Well, we didn't calculate the total cross section. We calculated the m squared, right? The amplitude squared. For the scattering of electron positron to say muon and anti-muon, or electron positron scattering. This is not a coincidence. What that scattering is the diagram below. So we have this diagram that we're calculating the imaginary part when Q is enough above the pair production threshold. Then there's an imaginary part, and that imaginary part is basically related to this diagram. This is the first instance of a large set of connections between different Feynman diagrams called optical theorems. It's a consequence of unitarity. We're going to go over that. Right? But is the observation clear? That when you do the calculation for vacuum polarization, when you're above the threshold, pair production threshold, there is an imaginary piece, and the imaginary piece when you calculate it is related to that. All right. This we should have anticipated. This is a consequence of the unitarity of the S matrix. So S dagger S has to be 1. Why is the S matrix unitary? Well, it's because it's just time evolution of the out to in to out. What we did was we took S and wrote it as 1 plus IT. Now, the fact that S dagger S is equal to 1 tells you that minus I T plus T dagger is equal to T dagger T. Right? That's just a consequence of the unitarity. Now, let's write down what that T is. Remember, T was basically what we did was that we wrote T as 4 pi. There was a conservation of external momenta, conservation of momenta, and then M. We call the rest of it M. So, what this left-hand side and right-hand side are equal to, for example, say in a 2 to 2 scattering, it would say that P1, P2, T bar, T dagger T of K1, K2 is equal to the right-hand side. This thing. Well, actually, no. First, what I've done is that I've done here. The first line is the first line is just the left hand, is the right hand side. I'm taking the right hand side and I just expanding it. What I do is first I put the resolution of identity. Right. So let me do it as board. So let me actually elaborate a little bit better. I don't have the pen, so it is a little bit tricky. Minus I T plus T dagger has to be T dagger T. So these, you know what they are related to, right? T's were one single T was related to one amplitude, right? This was appearing on an amplitude, so this would be minus I P1, P2, for instance. Oops, sorry. T of K1, K2, right? Minus P1, P2, dagger. Okay. Now, this is unfamiliar. We never really dealt with such a thing. So what we're going to do is that we're going to write it as an integral over, we're going to do a resolution of identity. So it becomes the multiplication of two amplitudes integrated over arbitrary final states. It's a resolution of identity. What we find is that the imaginary part of a particular diagram becomes related to the m squared of well, this expression. Let me massage it a little bit further. So far, everything's good. Everything is good. Okay. So here's what I was trying to say in words. This is the optical theorem. It says the square of the amplitude with arbitrary final state is related to the imaginary part of the amplitude if we take Pi equal Qi. Why do I have to take Pi equal to Qi? Because otherwise here I have Ki, sorry. Q1, P2. If I want to interpret this as scattering M norm of M, I have to pick this one to be the same as this. That's why. Right? When I look at that, then here it becomes P1, P2. Oh, it becomes P1, P2 here. This principle generalizes to arbitrary, from 2 to 2 scattering to arbitrary end-to-end scattering. So let me summarize it and say a little bit more generally. It's an observation regarding amplitudes, which is a consequence of unitarity. Below the pair production threshold, the amplitudes are real. The amplitude is real. Above it, it goes on shell. And then we have to use the IF sum prescription. Yeah, okay. The discontinuity, which is the twice I imaginary part of M, will be, we can diagrammatically draw it this way. Let me draw it. So here I'm writing it as if it's P and K. So it's imaginary part of this. It's relatively easy to understand there. It's the norm. This square. Right? And it's like cutting this open. Now I was in the previous line, I was drawing these guys up on the side. So I was talking about electron, positron going to muon, anti muon, right? But it doesn't matter. These are fine. The general rule of thumb is, as I said, is again, I tried to summarize it here. When you have the correction to a propagator below the per production threshold, everything is real and nice. Above the per production threshold, you'll find imaginary parts. The imaginary parts of that is related to the amplitude square of such processes. That's a consequence of unitarity. Good? All right, any questions? There's a lot that you could read off from that expression that we just calculated. This correction to propagator that we just calculated. Then let me write it on the board again. I'm gonna mess this up. I think minus 2 alpha squared over pi integral of d of x 0 to 1 x minus x. So this is what I call pi hat q squared. Pi of q squared minus pi of 0. This is ln of m squared over m squared minus x times 1 minus x q squared. Remember that this was delta of 0 and q squared. This was delta. Oh, sorry. No, this was delta of 0 and well, how did they call it? X and q, what did they call it? I don't remember. Anyway, this is the delta q squared equal to 0, right? And then this is the delta of q squared, right? This is the expression we have. What we can do next is, so we just talked about what happens when q squared is large enough that you could per-produce. What about the opposite limit? When q squared is very, very small, what are the lowest order corrections at low energies? When q squared is very small, energy is small, compared to what? Compared to mass, right? You are in the non-relativistic regime. What this is, remember that what we're doing is we're talking about charge normalization. This diagram tells you how strongly two electrons interact. Charge tells you how strongly two electrons interact. What is that in classical physics? It's the potential that we feel. What is the potential It's just E squared over 4 pi r. Right? So at very low energies, this is understood as quantum corrections to the Coulomb potential. You have two electrons, or electron positron, two electrons there. And there is this potential that tells you about classically the minus sign. Tells you how they interact. This tells you about the higher order, the first quantum corrections, QED corrections for this. There's a nice interpretation of it. We're going to use. All right. Because it's 1 over x, this is 1 over x. If you Fourier transform it, you're going to find this expression. So the potential that you expect, which is E squared over whatever, 4 pi absolute value of x, in Fourier space, it's going to be d3 of q, e to the power of I qx, e2 minus the renormalized charge over q squared. That q squared has to do with the Fourier transform of this. Now, the renormalized charge has this pi hat. Pi hat is a renormalization of charge, right? So that's what's down there. Good? Everyone follows? All right. So let's look at this expression and see how charge is normalized. The thing to stare at is this time. But now we're in the non-relativistic regime. So let me write it this way. Q squared over m squared. I can now expand in small q squared over m squared, right? And this is the expression you find, q squared over m squared. So what you find is the pi hat is 2 alpha over pi, 1/30th of q squared over m squared. This is how you could repackage it. So you find that the potential is changed by this extra term. This extra term, by the way, is related to Lamb shift. I leave it to you guys to figure out why it's related to Lamb shift. Can you tell why it's related to Lamb shift? What was Lamb shift? Do you remember? Lamb shift was when you were solving the Schrodinger equation for an electron orbiting nucleus in a background electric field. What is a background electric field? It's photons, right? So it's about how the presence of the photons changes the Coulomb interaction that we use to solve the Schrodinger equation. So at this level of approximation, I just took this term. It looks like it's short range. It's just a Dirac delta that pops up over there. If you do this a little bit more carefully, keeping this different distances in mind, so it's a couple of extra lines of algebra, but it's basically just different treating this properly, right? You end up with the following correction to the Coulomb potential. There are a couple of things. So it's first of all, the Coulomb potential is 1 over r. Here you find the potential, which is the first correction. There's an exponential fall off. Then down there you have r to the power of t over 2. Of course, the dimensionless quantity is mr, right? The correction is alpha squared. Does that make sense? Why is alpha squared? Can you see it? Why? Yeah, so this is a correction to this diagram, which was a 3-level interaction. This is order E squared. This is order E4. And alpha is E squared over 4 pi. Right? So that's the first order alpha correction. There's an exponential thing. Now, how are we going to interpret this? The interpretation is this. Two electrons were repelling each other, for example. Or electron and positron were attracting each other. This is sort of a cloud surrounding, a cloud of fermion, antifermion surrounding each of these guys, resulting in dipoles or higher moments that give you this potential. Now, so it means that the vacuum of QED is like a dielectric medium due to quantum fluctuations. These are quantum fluctuations, honest to goodness quantum fluctuations. And in particular, because we're in the low energy limit, they never go on shell. We're not even close to pair producing. We're not even close to the threshold. There is a very, very important message here. The sign of the correction to the potential. What does it tell you? Does the charge increase or decrease? The effective charge increases as a result of quantum corrections. At lower and low energies, the interaction gets stronger and stronger. Wait, no. The other way around. Sorry, this is the opposite. I should be corrected, but my pen doesn't write. At high energies, the interaction is stronger. Why is that? Because we're comparing the interaction at scale q squared with interaction at scale 0. Yeah, sorry, this is a typo. All right, any questions about this? Now I should go to the previous file. Optical theorem here. All right, any questions about this? So this finishes the calculation of the vacuum polarization and its interpretation. I'm still going to ask again, are there any questions about the interpretation of vacuum polarization calculation? We have 2 more calculations to do. We'll probably have time to do one of them. Fermion self-energy and the vertex corrections. We're going to start with the fermion self-energy. And I drew the diagram a million times. The 1pi diagram at one loop is just this thing. This is what we're going to calculate. But as usual, you see the resummation of the 1pi diagrams will give you the following structure, right? The propagator will become p slash minus I. This is the 1pi amplitude. The point of 1pi is that you always put it, when you have 1pi diagrams, the 1pi diagrams become a renormalization of mass. For the photon, there was no mass, essentially, importantly. So we interpret as a normalization of charge through the other diagram. But here's a normalization of mass. if we calculate this diagram, we're going to be renormalizing the mass of the fermion. All right, now it's important to realize that the sigma of P is a matrix with spin indices because we're dealing with fermions, right? What we're calculating is the order alpha corrections. Alpha is E squared, right? And this is supposed to be the 2-point function, the propagator, right? Well, in Fourier after Fourier transform, actually, yeah. This is supposed to be this guy. There is also room for some overall constant here, Z2. Remember for this is to be compared with the photon thing. In the case of photon, what happened was that there was a Z3, right? And then Q squared. There was no normalization of mass. The Z3 had something down here, which was pi hat, and I just put up there. The poles didn't change. There was no pole. There was no pole. So I just interpret it as these three, right? But here, what? Yeah, okay. The whole thing was multiplying Q squared. So the difference between these two terms is that this is it's multiplying the whole thing, right? But this is just a shift. So this is called the wave function renormalization. Oh, sorry. It's called the wave function renormalization, and this is a mass renormalization. All right. So what does the diagram look like? Let's see if by staring at it, you can see it. This is when it's helpful to have the pen. But okay. So what does the diagram look like? The diagram will have two nodes. So there's minus IE gamma mu here, minus IE gamma mu here, right? Those are the two terms. There's a fermion propagated in the middle. There's that ISF. So do I not have the? Yeah, I have it. QK. Yeah. So this is Q, this is K, this is Q minus K, and this is Q. Right? So there would be the fermion propagator, ISF of Q minus K in the middle, right? What's the point of that eta mu nu minus K mu over K squared? What's the point of that? It's a photon propagator. So the photon propagator is I over K squared, but you have to make sure that it's transverse, right? So that's why you have it. Okay, as usual with the fermion, what you do, the trick is, as we've done this several times, we first write it. So it's the fermion has I over, what is it? Q slash minus K slash minus M plus M plus I epsilon, right? So we first write it as this guy squared and then put the Q slash plus K slash up here, plus M, right? Now use the trace technology to simplify things. There will be a bunch of gamma matrices that you'll have to deal with. The expression you find, this is so helpful to have a pen at this point. The expression you find is the second line. Okay? That's what you find. Once you use your trace technology, in the parentheses, you'll identify two terms. So what are the steps you have before going through all of that? Yeah, the set of tools and techniques are the same. We're going to do Feynman trait parameterization. What are we going to do that to? We're going to do that to the propagators that's I over k squared, right? And then 1 over or I over k minus q squared plus m squared. Right, that's what we're going to do. So it's 1 over AB. Maybe. We'll see that in a second. All right. There are two terms. So first, let's focus on the very first term. This is what it looks like. Oh, another thing is that I instantly also wrote it in, I wick rotated. I don't really need to do much for that. And second, I did dimensional regularization. I introduced a mu to a power of 4 minus d plus epsilon and then changed my integrals to d plus 1. But notice that here, when I did in the third line, when I use my trace technology, now because there are gamma matrices in d plus 1 dimensions, I have these factors of d minus 1 coming out. Right? Any questions? So let's focus on the first term. And what we're going to do is we're going to use the Feynman parameterization. The Feynman parameterization will give us this expression, integral 0 to dx. What is downstairs, right? I'm only treating the first term, the I term, the one or whatever. Yeah. Can you see where we're think how this expression comes about? There's some algebra, of course, that we'll take care of, but structurally still is the same. There is a delta, right? And delta is, once again, previously what was delta? Delta before was m squared minus x times 1 minus x cubed squared. Has the energy scale of energy, right? This is the on-shell external momenta that we've shifted by some constant, right? It's still the same, but there's an x now. Wait, what? I'm misremembering? Wasn't my delta this in the previous example? No, I think I'm pretty sure that was a delta anyway. Yeah, I'm pretty sure that's a delta. Yep. There are various Feynman parameterization. Let me just actually say that as well, because it's the last lecture. So the Feynman parameterization we wrote, we used was this. But now in this example, the Feynman parameterization we need is this. There is more generally Feynman parameterizations for things like that. People do better for these. For QED diagrams, there is this that we use, there is this that we use, there is 1 over ABC that we'll have to use. But I don't think I'll get to the third one. This guy, you would not be surprised to know that it gives you two integrals, dx and dy. But we're only doing 1 over AB squared, so there's only one of x. Okay, so you do your change of variables, you define this L mu. Now you could explicitly do the integral over the over the external, over the momentum inside, right? The loop. You do the loop integral now, and the structure of it looks like this last line. Well, I don't have a. Right. As usual, the result of the integral, we're only treating that first term. The result of the integral will give you a bunch of gamma functions, right? Again, the calculations are structurally similar. Now, what did it look like before? Just want to make comparisons. Before, it looked like this. It looked like integral of d of x from 0 to 1, x times 1 minus x, right? ln of 4 pi e minus, well, actually, there was a 2 over gamma, 2 over epsilon. I've done that expansion. Yeah, okay, so that's not a very fair comparison. Here what happens is that you end up with a q slash upstairs. That shouldn't surprise you. There's also d minus 1. That d minus 1 will give you what? Will give you a term that's order epsilon, right? So those are the things that you want to keep track of. Those terms are suppressed. You further massage this, and this is what you obtain. Expanding in the 1 over epsilon, you end up with 2 over epsilon. Well, this is now what I want you to see. 2 over epsilon plus ln of 4 pi e to minus gamma mu square over delta x. That piece is identical to the piece that we found before. What sits outside is minus alpha over 2 pi. That's a little bit different. It was minus 2 alpha over pi before, so there's a factor of 4 sitting there. There's an overall factor, which is 1 minus x times q slash minus 2m. We did not have that. Good. And then there's the last term, which is plus m minus 1 minus x q slash. So the divergent term is the divergent term. Well, I'm not going to discuss the MS bar prime actually. So I just want to finish this calculation. But are there any questions about that? So this is what I wanted to compare. So that we did the second integral, all the same tricks, a little bit more involved. I didn't go through them in detail, but you could do you should do them by yourself. This is what you find. Now let's go back and do the calculation for the second term. This term. So the this first term involved doing some sort of a Feynman trick like this. The other one, let me see if I can. Yeah. The other one, you'll use this Feynman trick. 1 over a squared b. Actually, I think in the previous example, what I did was I used this, which is the old Feynman trick squared. So here's a Feynman trick used for this one. You do your usual tricks. You do dimensional regularization, d plus 1. You change the variable. You introduce this new loop variable L mu. You do Wick contraction, Wick rotation, and then d plus 1 is 4 minus epsilon. You go through all of that, and this is the final expression you get for the second term. Again, I'm not going to try to explain the MS bar prime. So let me not, this is an intermediate thing that I wrote. You put the two terms together. This is the structure you find. Actually, maybe. No, let me comment here. So this is what it looked like, right? There is a divergent piece. That's this one. So this term is divergent, and this term is clearly one order lower. This is the piece that will survive, gives us a constant. The MS bar prime, this MS bar prime is what I was just trying to tell you, that you could eat this ln piece in a redefinition of epsilon. This is the standard way of doing calculation. It's a convention that is often used as a form of regularization. You do dimensional regularization, but instead of keeping track of things in terms of epsilon, which is d plus 1 minus 4, or sorry, 4 minus d plus 1. Yeah, 4 minus d plus 1. What you do is you introduce epsilon. Gamma is a fixed number, is whatever it's called. You introduce epsilon bar, and now you package the divergences in terms of 1 over epsilon bar. This scheme is a regularization scheme. It's called MS bar scheme. What it does for you is the following. In renormalization, you saw that when we do the subtraction, this term just drops off. And you end up with only this ln of mu squared over delta. What we want to do is, when you do MS bar scheme, without even doing the subtraction, you identify the crucial bits. Right? That's just a convention. Okay. You add both of them, both of the diagrams, and this is what you obtain. The total structure of this one loop calculation will give you a piece that is 1 over epsilon bar divergent, 3m alpha over 2 pi, right? Plus alpha over 4 pi m times 4 plus ln of mu squared over m squared. Now, I have done some simplifications. What is the simplification? You can see that this expression, that's order epsilon here, has minus mx squared q squared over delta. Right? So the simplification I've done is I've taken q to be exactly m on the node because I want to interpret this, but I don't have to. Why am I doing that? Let me elaborate a little bit. I think I have to explain this. What we're after, I erased it. We're after the renormalization of the mass. What is the renormalized mass? The renormalized mass is the pole of the one loop propagator, right? Sorry, the pole of the propagator. This is the propagator, right? We wrote this as I over q slash minus m, or plus m, minus m, minus the 1 pi propagator. Everybody's with me? It's just a resummation. Now, this I calculated up to 1 loop. Good? So this is what the calculation is. And it gives me minus m minus sigma of q slash. All right, so this is problem. What's the renormalized mass? It's the pole of this thing. That pole better be m. So at q slash equal to m, this thing will be 0. Right? I don't know if I want to walk you through this algebra, but let me. Well, you can see it in the notes, but how do I want to do this? So first observation is mass renormalization is infinite, right? Shouldn't be surprising. Charge normalization was infinite as well. The thing that's physical is the subtraction. So we define mass ms bar, right? This is some divergent mass that we've defined. We normalize divergent mass. So what we're gonna do is that we're gonna write down the pole in terms of this ms bar. Because it makes the dependence on mu squared explicit. I could still do the exact same thing that I did before I defined pi hat pi of q squared minus pi of 0. But this is a convention that people usually use. What you need to do is you just need to have a way of making sense of the divergent piece and keep track of the finite piece, right? And ms bar scheme is one way of doing such a thing. At the end of the day, how you split it, it doesn't matter because the physical thing is not mass of the pole, but it's the running of it. Good? Questions? But let's look at the structure. Actually, maybe it's worth mentioning the structure of this. It's of course proportional to alpha over 4 pi. Actually, I'm not sure if I want to say much about that. So, okay, I'm not doing normalization. This is all in anticipation of discussing renormalization. I won't do that. All right. I have a couple of minutes to say a few words about the vertex correction diagram. But before saying that, because I might run out of time, let me repeat all the crucial ingredients of these kind of loop diagrams. So we did 2 propagator corrections, right? I just raised it, right? So these propagator corrections take these form. So in this case, it would be q squared z2. I call it the z3. And this is I z2. You want to put I epsilon or not. This is q slash minus m minus sigma. There's a normalization of mass and there's a normalization of the wave function. This is P of psi bar. Right? That's the propagator of the photon. P of mu. All right. So now the vertex is a little bit more complex. Oh, sorry. To do these integrals, the set of tricks that we went through was there was an integral over d of k. We did dimensional regularization like this, right? If you had, in this case, you had a bunch of gamma matrices, so you had to use your trace technology. But that's upstairs in the numerator. Down here in the denominator, we have factors that look like this, propagator, right? There's q q squared minus different m's, right? Here you use the Feynman parameterization. Sometimes terms look like this, sometimes terms look like this, depending on up here what orders of things you have. In this diagram, well, actually, yeah. All right. That will give you a bunch of integrals, d of x or d of y, a bunch of integrals out. You change the order of integration, you define a new variable, right? And then you perform the integral over these, you get a bunch of Gauss matrices. Those Gauss matrices have poles exactly on 4 dimensions. In the gauge theory case, we saw case situation that there were terms that were violating gauge invariance, but they were canceling, and they were 0. And the way to see it was to go off the real pole by dimensional regularizing and seeing that they cancel, right? So they were 0. The remaining term is always log divergent. Keep that always in mind. There's always a form of log divergence. All of these expressions that we have, there are ln deltas on over deltas. They're log divergences. And then we do expand in small epsilon. There is a 1 over epsilon piece that comes out. Often we write it in terms of this MS bar scheme, which is just a redefinition. Oh, and I forget this, something like this. That's a particular constant we shifted by, right? And then what you obtain is an expression. Now, there are divergences. You subtract 2 terms to see the running. You have to appropriately interpret this. In this case, we interpreted the Z3 as a renormalization of charge. Here, it is a renormalization of mass, renormalization of the wave function. Unfortunately, we won't have time in this course to do renormalization properly, but there's a whole theory that takes care of all of this stuff. Let me just, in a couple of minutes, say a few words about the last diagram of QED. So the last diagram of QED is this diagram. Now, this is the most involved one, and there are a whole bunch of things that are important about this diagram. So what was this? What was this? This was minus I E gamma mu. This is going to be a correction to that. So let's just write it. Minus I E lambda. Lambda, I call it lambda. Now you already have some clue that there is a renormalization of charge that's going to be related to this. So there is a connection between this diagram and the polarization, vacuum polarization, right? Here's what this expression looks like. There are 2 fermion propagators, right? There are 2 SFs in there. There are 3 gammas, right? Another thing that you notice is this order EQ. Not surprising, because this correction to the next order is going to be E times something that's 1 plus E squared something, right? It's a 1 loop correction. Now, let's do dimensional counting of how the divergences work. In 4 dimensions, the integral over P is lambda 4. There are 2 fermion propagators, each of them is 1 over lambda, and then there's a photon propagator, which is 1 over lambda squared, so it's log divergence. Always we get log. Sometimes we get at higher orders in perturbation theory, we sometimes get log squared. We'll do an example of that in part 2 of the course. The log divergences are the essence of renormalization. Now, all right, how much do I want to say about this? Let me see if there's one thing I can, if I want to say one thing about this diagram, what would it be? Well, first you have to do the Feynman parameterization on 1 over ABC. Yeah, okay. So you have to use a bunch of new identities, but yeah, I'll stop here. I'll just say that we did some sample calculations of one loop diagram. I don't expect you guys to understand all the physics of it, but at least you have an in principle way of doing it, and you know the tricks, right? So you could open Peskin or any other textbook. There's a one loop diagram, whether it's scalar or QED. You could keep track of them. First, you can write them down. Then all the tricks that are used are familiar. These are pretty much the only tricks at the one loop level. Fancier theories have fancier tricks, require fancier tricks. All right? There are divergences that appear, but we said the divergences have to do with the fact that the parameters in the Lagrangians are unphysical. The physical observables are going to be the low energy ones that are independent of the cutoff. Right? Yeah, I think I'll stop here and ask for questions. All right. Yeah, thank you so much. I think this is the end of this semester. I think in the future, if I'm teaching this, probably I will stick to only one loop diagram. I feel I can't do justice to it because I'll have to do this properly all next semester anyway. So, yeah.